let's jump right in. I want you to picture something incredibly simple. Just imagine dropping a regular drinking straw inside a slightly wider plastic tube. You know that empty, ring-shaped gap of space right between them? Well, that right there is called an annulus. Now take that exact same idea and scale it way, way up to a massive industrial level. Picture a solid steel drill pipe sitting inside a wellbore that plunges literally 2 miles deep into the earth. It's wild to think about, but every single thing you drill down there has to come all the way back up to the surface through that exact gap. Every rock cutting, every ounce of drilling mud, and, if things go wrong, every cubic foot of highly pressurized gas. It is absolutely the most important empty space on the entire rig, and understanding it is the true key to mastering wellbore geometry.
Okay, so let's get into exactly what this is. The annulus is, at its core, the space around a pipe inside a wellbore. But here is the critical part to remember. Its inner wall is always the outside of the pipe. The outer wall, on the other hand, can change. Sometimes it's the raw exposed borehole cut right through the rock, and other times it's the inside of a steel casing string that's already been cemented permanently into place. Basically, anytime you have one pipe sitting inside something larger, that ring between them, that's your annulus. And what's really fascinating here is that we are defining a vital function based entirely on empty space. I mean, the annulus isn't a tool you can just pick up and hold in your hands. It's literally a void.
So, how does this actually work when we're drilling? It's all about a continuous circulation loop, which is honestly what keeps a well alive. First off, your drilling fluid, which we call mud, gets pumped straight down the inside of the drill pipe. Then it blasts out under immense pressure through the nozzles at the drill bit all the way at the bottom of the hole. And finally, this is where it gets interesting. It has only one route home. It has to travel all the way back up that annulus. On its journey up, it's doing a lot of heavy lifting. It's carrying all the crushed rock and cuttings to the surface, it's cooling the drill bit, and the sheer weight of that mud column is physically pressing against the walls to hold back the Earth's natural pressure. If you were to somehow block the annulus, that entire loop stops dead, and the well stops working in a matter of seconds.
Now, a finished well isn't just one single pipe in one hole. It actually telescopes down and features several nested casing strings, kind of like Russian nesting dolls, which means you're dealing with multiple annuli, and the industry has a really smart way of naming them. We just go from the inside out. So the A annulus is the gap between the production tubing and the production casing. That's the one a producing well deals with every single day. Stepping out one layer, you've got the B annulus sitting between the production casing and the intermediate casing, and then the C annulus sits just outside of that. This naming system is brilliant because of how efficient it is. If an engineer walks into a room and says, "Hey, we have pressure on the B annulus," every single person instantly knows exactly which ring of steel is leaking without needing a single extra word of explanation.
Now what's really interesting here is this very specific number, 1029.4. This is the absolute bedrock of the formula every driller uses to calculate annular volume. Let's walk through the math real quick. To find the volume in barrels per foot, you take your hole diameter squared, subtract the pipe diameter squared, and then divide that whole result by 1029.4. Let's try it with some real numbers. Say you've got a 12¼ inch hole with a 5-inch drill pipe. 12.25 squared is roughly 150. 5 squared is 25. Subtract those, and you're left with 125. Divide that by our magic constant of 1029.4, and you get about 0.12 barrels per foot. It's such a simple, elegant piece of math, but it gives you total visibility into an invisible space thousands of feet underground.
So, you might be wondering, why do we care so much about calculating that exact volume? Well, knowing your annular volume tells you exactly how much mud should be coming back to the surface. If the volume of mud returning doesn't perfectly match the volume of mud you just pumped down, you are in a serious emergency situation. It means one of two extreme things is happening. Either you are losing your incredibly expensive fluid into cracks in the rock formation, which we call losses, or much worse, the formation is actively pushing its own fluids, like highly pressurized gas, into your annulus. We call that a kick. Both of these scenarios are massive, stop-everything emergencies. That simple calculation we just went over, that is literally your very first line of defense against a blowout.
To really grasp how engineers manage this space, I want you to think of a garden hose that's been shoved down a blocked drain pipe. When you turn on the tap, the water goes down the hose, and the only way out is the ring of space around it, dragging wet leaves and grit up along with it. If you have a narrow annulus, you're squeezing that returning fluid into a much smaller gap. Because of that, the flow speeds up, carrying debris out super efficiently and giving you a really clean hole. But on the flip side, if the annulus gets too wide, the flow slows way down. When that happens, the rock cuttings and debris settle out of the fluid. They pile up, and eventually they can pack off the well entirely. Engineers are constantly juggling this exact trade-off. They need the fluid velocity high enough to clean the hole,
but absolutely not so high that the pump friction actually fractures and breaks the rock.
Okay, I want to test your intuition for a second here. Let's say you're drilling away, and you decide to swap to a larger diameter drill pipe. You put it in the exact same sized hole, and you run your mud pumps at the exact same rate. Does the mud travel up the annulus faster or slower? Seriously, think about it for a moment. Try to actively picture that geometry in your head. Same hole, but a bigger pipe inside of it. What happens to the speed of that fluid trying to escape?
Well, if you guessed faster, you hit the nail on the head. A bigger pipe obviously means a smaller annular gap, and when you force the exact same volume of fluid through less space, it has absolutely no choice but to speed up. Now on the surface, that sounds fantastic for carrying those heavy rock cuttings out, right? But remember, it's a real double-edged sword in well engineering. Faster mud flow means a whole lot more friction pressure scraping against the bare rock wall of the hole. If that friction pressure gets just a bit too high, it can easily fracture a weak rock formation, creating an entirely new set of disastrous problems. Every single annulus out there represents this incredibly delicate balancing act between cleaning the hole out and accidentally breaking the hole apart.
We've covered a lot of ground in this explainer today, taking this whole concept from a simple straw and a cup all the way to high-stakes well control and fluid dynamics. And I want to leave you with his final thought. The annulus isn't a pump, it's not a steel valve, it's not some tangible piece of equipment you can just point to on a manufacturer's blueprint. Yet it entirely dictates the size of your casing, the speed of your pumps, the strength of your wellhead, and honestly, the very safety of the rig crew. It is this high-stakes, completely empty space that every single piece of equipment on the rig is built around. Understanding the annulus is about understanding the environment where all the actual work of drilling takes place. It kind of makes you wonder, doesn't it? What other invisible, empty spaces are out there secretly dictating the absolute rules of the world's biggest industries?